All right, let's talk about how you approach this. So someone gives you a polynomial and they want you to factor it, which you might have to do if you're trying to use partial fractions. There's a theorem in math that says if a polynomial factors and it has like nice integer or rational pieces to it, like factors or solutions, they have to be a factor of this constant here. The theorem is actually a little more complicated than that. It says they have to be a factor of this divided by a factor of the leading coefficient. But since the leading coefficient is 1, that doesn't really change anything. So the possible zeros of this polynomial, it's actually called the rational zeros theorem, in case you care. The possible zeros for this are plus or minus 1, plus or minus 2, plus or minus 4. And so the easy way to try and factor this is just start plugging things in and see what you get. If I plug in 1, which is where I'd always start, well, if I plug in 1, what do I get? I get 1 plus 2 minus 7 plus 4 equals 0. So if I plug in a number and get it equal to 0, it means that x minus that number is a factor. So I can factor this as x cubed plus 2x squared minus 7x plus 4. I should get x minus 1 as a factor. And then you can find the rest of it by either doing polynomial division, or if you remember it's synthetic division. Nobody remembers synthetic division. Or you can just kind of work it out. I know I need an x squared here to multiply by x to get x cubed. But then the minus 1 is going to multiply by x and give me a minus x squared. But I need a 2x squared there. So I need to add on a 3x. So that 3x times x will give me 3x squared minus x squared will give me 2x squared. But then the 3x times minus 1 is going to give me a minus 3x. But I need a minus 7x. So I need a plus 4 here. Plus 4? Yeah, plus 4, I guess so. We'll have to double check this in a second to make sure it works. Let's see. I feel like no, that seems right. Oh, no, it's a minus 4. Because I need a minus 4 times x to give me a minus 4x and a minus 1 times 3x to give me a minus 7x. Plus the minus 4 times minus 1 should multiply to positive 4. And then we can look at this, and it's a quadratic thing, which we can factor in a usual sort of way. So this is going to be x minus 1 times this factors as x minus 1 times x plus 4. There are lots of ways to factor polynomials. The reason I bring this up because on one of the homework assignments, there's a question that says something to the effect of, it's not exactly like this, but it's similar. Find the volume of the solid obtained by revolving y equal to the square root of some gross thing. What have I got here? I made something up that was gross. 4x squared plus 9x minus 3 divided by x cubed plus 2x squared minus 7x plus 4 plus 2x e to the x squared around the x-axis, which is really disgusting looking, but it's not as bad as it looks once you break it down into its constituent parts. So let's break it down and see what happens. So first of all, yeah, that function looks terrible, but you're not being asked to find the area under it. You're being asked to find the volume, which means you get to square it. So if I draw a quote unquote picture here, and again, my picture is not going to be very realistic, but I've got, sorry, I forgot one piece of information here. Around the x-axis, between x equals 2 and x equals 5. So we've got some sort of wacky looking function. And I'm going to pretend like it looks like it's always positive. I don't actually know. And we're going to revolve this thing around the x-axis between x equals 2 and x equals 5. So we're just getting some sort of usual disk method sort of thing. There's no good reason to draw this picture other than I felt like drawing a picture. But we're getting some sort of volume, and actually there is one good reason. See what the slices look like. our slices are just discs. And the volume of my disc is just pi times the radius squared times a small change in x. Or as I would say, pi times the radius squared, where that's your radius, it's how far you are from the x-axis. And that small change in x is just the width or the thickness of your slice there. Questions? Yeah, still yes, wild guess. I'm sure this is absolutely not even close to what it looks like. But I don't really care. We don't really need to know what the graph looks like. I should say, if they tell us what the limits of integration are here. If they don't tell, like if they give us a more reasonable graph and ask us to like find limits of integration, yeah, we might need to graph it or to kind of see what the boundaries actually look like. But here they're just telling us the height of the function is this, that's your radius, do the usual thing. So to set this up, and I'll point out for those of you that are in what's this Goldsmith's class that has a question like this, I think. Is anyone here in Goldsmith's class? Yeah. There's a question similar-ish to this on your homework, I believe, where you have like a square of some terrible thing. There was a point. Oh, he kind of has you do it in the opposite order. Like he has you do the bits and pieces first, and then tries to put it all together at the end, which is totally great. I'm kind of working the backwards way and starting off with the gross thing, and we'll talk about how the individual pieces work out here. So if I was going to find the volume, the total volume is just going to be the integral from x equals 2 to x equals 5 of pi times our radius squared. But our radius is our function, which I wrote over there. And right, our radius is the square root of all that stuff squared. I don't really want to write it again, but I guess I will. 4x squared plus 9x minus 3 over x cubed plus 2x squared minus 7x plus 4 plus 2x e to the x squared. But the point of this is that when you square the square root, they undo each other. And so we're really looking at finding this thing, which is going to be equal to pi times the integral from 2 to 5 of this piece here, 4x squared plus 9x minus 3 over x cubed plus 2x squared minus 7x plus 4 plus this piece over here. And really what we should do here is find these indefinite integrals separately. We should find each of these antiderivatives using whatever processes are necessary, and then go back and actually plug it into this whole situation up here. So let's go ahead and deal with the easier one first. Let's find the antiderivative of 2x e to the x squared. I'm just going to do the indefinite integral because I'm going to do it all at the end. So this is a mixture. I've got a power of x and an exponential thing. And the mixture means I should either use a u substitution, or if that doesn't work, I should use IBP, integration by parts. But you should always try to see if there's an easy u sub first, because that's usually easier. So let's see, is there a good choice for you here? I believe there is. What's a good potential choice for you? Yeah, there's actually technically two good choices here. X squared is the choice I would make and I would encourage you to make, but you can also actually choose e to the x squared as your choice for you. But when you have options for you, I would encourage you to pick the simpler thing because it's usually easier to deal with. So if u is x squared, our du is exactly 2x times dx. So this integral is going to become the integral of just, again, I would encourage you to think about this part first. That 2x times dx is just du. So there's my du dealt with. And now the e to the x squared, well, x squared is u. That's going to be e to the u. We integrate, we get e to the u. I don't really care about the plus c here, although there is a plus c. And then finally, I plug back in what u is equal to, and I get e to the x squared plus c. And that is the antiderivative of 2x e to the x squared. So when I do this integral over here, I'm going to get something here plus e to the x squared there, and then plug in 2 and 5 and subtract. Actually, 5 and 2, I should say, right? 5 first, 2 second. Let's deal with the other piece, which is much less nice. Everyone cool with this? Yeah, Lala.
What are you gonna do with that? What you just got right there?
This stuff up here or this stuff down here?
No, we can just square it.
So the thing is here, I'm looking at this integral here and seeing that I'm gonna have to integrate or anti-differentiate both this piece, which I haven't gotten to yet, plus this piece here. I was just dealing with this piece here. The integral of 2x e to the x squared is this stuff over here, which gave me e to the x squared plus c. So when I do the antiderivative of this, I'm going to get whatever the antiderivative of this is plus e to the x squared. I'm not going to write the plus c part because it's going to be definite. So I've dealt with this half of it. You could, even if you really wanted to, break it up, right? You could write this as the integral of this plus the integral of this. We don't need to, but we could. Other questions about this? And if you're not sure that this is actually right, you could always take the derivative. The derivative of e to the stuff is e to the stuff times the derivative of that stuff, which is exactly e to the x squared times 2x. So it totally works out. All right, let's look at the other piece, which is why we started factoring that terrible thing in the first place. So the other piece certainly doesn't look like a u sub is going to work out, although you should always check, or at least think about checking. If I'm looking at 4x squared plus 9x minus 3 over x cubed plus 2x squared minus 7x plus 4. If I took the derivative of that bottom, like if I thought of letting u equal the bottom, my du would be 3x squared. Okay, let me write it down just so I can get it out of the way. If I thought u could be x cubed plus 2x squared minus 7x plus 4, my du would then have to be 3x squared plus 4x minus 7. Sometimes this does work if you can multiply all of this by one constant to get all of that. And if you're not sure if it works, figure out what you need to multiply 3 by to get 4 and then multiply the whole thing by that. So if you multiply 3 by 4/3, you get 4, but 4 times 4/3 is not 9, so it's not going to work out. But I saw someone with a problem like this where like you had to multiply everything by like 3/2 or something, and then it all did work out. So definitely it is worth checking. Sometimes it works out. Look for the easy u sub. Don't do partial fractions if you can do a u sub. Okay, so u sub not going to work. Bummer. Partial fractions. So I know it's partial fractions because 1, it's a rational function. 2, the degree on top is, how does the degree on top compare to the degree on the bottom? Smaller than, not equal to, strictly smaller than. If it was equal or bigger, then you'd have to do polynomial division first. And then lastly, the denominator does factor. We just factored it at the beginning of class. I forgot what it was already. I think it was x minus 1 squared. Maybe x plus 1 squared. I don't honestly remember. Let me go look. It was x minus 1 times x minus 1 times x plus 4. So x minus 1 squared times x plus 4. And now we're going to write down the partial fraction decomposition. So the x minus 1 squared is a linear factor. Oh my gosh, is a repeated linear factor. So I need that highest power of it. So a over x minus 1 squared. And every lesser power down to 1. So I need a b over x minus 1. And then I also need a c over x plus 4. It does not matter which order you write these in. I tend to just look at them from left to right and go from higher to lower powers. But if you wrote a over x plus 4 plus b over x minus 1 plus c over x, it doesn't matter, right? As long as you have all of these pieces you need, it doesn't matter what letters you're using here. Oh, sure. Yeah, of course. Yeah, go ahead. I don't think I need to do anything there. Cool. Yeah. The key step here that I think people tend to forget is that this juncture, you have to multiply both sides by the common denominator. So I'm going to multiply both the left and right by x minus 1 squared times x plus 4. And the left-hand side, or the thing you started with, is always going to have the same result. You're going to get just the numerator. So on the left-hand side, we're going to get 4x squared plus 9x minus 3. On the right-hand side, if I distribute here, I shouldn't get any denominators. That's the whole point of multiplying by the common denominator, is that all the denominators should cancel out. So I multiply this by that, the x minus 1 squared cancels, and I'm left with a times x plus 4. When you multiply here, the x minus 1 of the x minus 1s cancel, and I get b times x minus 1 times x plus 4. And multiply here, the x plus 4 cancels, we get c times x minus 1 squared. There's a number of ways of doing the rest of this. I know I was talking to someone, I don't know what class they're in. They're in, I think, they were in Alvarado, Goldsmith's class. They were trying to do this appropriately by just equating coefficients, which is a totally fine way of doing it, but it's harder that way. Or it's not that it's harder that way, it's you're not taking advantage of the easier method, which is saying the same thing, really, I guess. The easy way of doing this, the thing you should always do before you do anything else when you're doing a partial fraction decomposition is use the easy values of x. There are two easy values of x I should use here. What are they? Actually, don't tell me, write them down. There are two things you should write down, x equals something and x equals something else. I'll give you 20 seconds. Okay, it's been 20 seconds. The two things you should be picking for x are x equal to 1 and x equal to -4. The values of x that are going to make some of these factors 0. So if I plug in x equal to 1, I have to plug it in everywhere. So I'm going to get 4 plus 9 minus 3 on the left equal to a times 1 plus 4 plus 0 plus 0. I'm not going to write those down. 4 plus 9 is 13. 13 minus 3 is 10. So I have 10 equal to 5a, which gives me 2 equal to a. Great. Clearly someone thought about this problem if the numbers are turning out nicely. All right. Also, it's a pretty good bet that if you've got a gross partial fractions problem like that, your coefficients are probably going to turn out to be nice integers because someone did the work to make the problem not suck. Let's plug in -4. So -4. Okay, so I mean 4 times 16, 9 times -4 is -36 minus 3 equals a times 0 plus b times 0 plus c times -4 minus 1 is -5 squared. 4 times 16 is 64. 64 minus 36 is going to be 28. Minus 3 is 25. Equal to c times 25. Well, that worked out nicely. C is going to be 1. And now here's where you have a choice. And I would probably say I don't like making this choice. It's not my favorite thing to do. I would much rather prefer at this point to equate coefficients because I think it's elegant. But if you only have one thing left to find, right? I found A, I found C, I only have to find B now. It's probably easier just to plug in another value for X and plug in your known values of A and C and solve for B. And of course, since I haven't even used X equals 0 yet, that is definitely the value you should pick. So if you haven't used X equals 0, I'm gonna say it again, you should use X equals 0 to find the last thing. So if I plug in X equal to 0 and A equal to 2 and C equal to 1, I'm going to get 0 plus 0 minus 3 equal to 2 times 0 plus 4 plus B times 0 minus 1 times 0 plus 4 plus C, which is 1 times 0 minus 1 squared. That is not terrible to solve. I've got -3 equal to 8 minus 4B plus 1. Gosh, my B's always look like 13s. Try to be careful with your capital B's and make them not look like 13s. And then let's see. 1 plus 8 is 9, right? Yeah. And then -3 minus 9 is -12. So -12 equals -4 times B. So 3 is going to be what B is equal to. Yeah. I will just point out, because I think it is cooler, that we could have also found B by saying, if we look at the coefficient of x squared, on the left-hand side, we have a 4x squared. On the right-hand side, we have no a times x squared, right? You have an a times x and a times 4. You would have a b times x squared, and you would have a c times x squared. And then since we know that c is equal to 1, b has to be 3. I just think that's a cooler way of doing it. Do we need to be cool when we do math? No, but it's fine. So it's also, I will say this way is nicer if you have more than one thing left to find. It is often easier to work with these coefficients of powers of x than it is to work with plugging in lots of different things to find. Or also, if your numbers are not like nice integers, like if you've got fractions, then it can get really dicey to plug in other numbers to try and solve for that. So at the end of the day, you can do it whatever way you like, but this is how I would do it. All right. It always feels like a bummer with partial fractions because you've done all the work to do the thing, and then you still have to integrate the thing after you've done all the work. So just to point out here, now we're going to say that the integral, are we going to say? Yes, we are. We're going to say that the integral of 4x squared plus 9x minus 3 over x cubed plus 2x squared minus 7x plus 4 is equal to a, which was, what was it? 2 over x minus 1 squared. Sorry, the integral of 2 over x minus 1 squared plus b, which was 3 over x minus 1 plus c, which was 1. Yeah, over x plus 4. Which is much easier to integrate. The things that are to powers of 1, like the x minus 1 and the x plus 4, those are just going to give you antiderivatives that are natural logs. But this one here is a little bit different. I would rewrite this as the integral of 2 times x minus 1 to the negative 2 plus 3 times 1 over x minus 1 plus 1 over x plus 4. And then when I integrate that, I get 2 times x minus 1 to the negative 1 over negative 1 plus 3 times the natural log of the absolute value of x minus 1 plus absolute values, and then plus the natural log of the absolute value of x plus 4 plus c. What I'm skipping here is doing the tiny u substitution of letting u equal x minus 1, du equals dx. So the integral of 2 times x minus 1 to the negative 2 becomes the integral of 2 times u to the negative 2 du, which then becomes 2u to the negative 1 over negative 1, which then becomes 2 times x minus 1 to the negative 1 over negative 1. I think you can get away without doing that u substitution if you are comfortable with it. But if you're not, it's also okay to do the u substitution. Okay. We've done all the bits and pieces. Now it's time to go back and find the definite integral that represents the volume of this thing revolved around the x-axis. So now we're going to go back and say, all right, our volume is equal to pi. Don't forget the pi. It's really easy to forget the pi if you've done all this other stuff. Don't forget the pi. Almost Halloween. Don't forget the pumpkin pie, right? That doesn't really work. It's trying. You never want to forget the pie. It's tasty. Right, so anyway, and then we were integrating this garbage here. 4x squared plus 9. I'm just writing the original thing here. Well, not really. I squared it, I guess. Over x cubed plus 2x squared minus 7x plus 4 plus 2x e to the x squared dx. And then all we're going to do is we're going to say, I don't need to write the work again. I'm just going to jump to my integral or my antiderivative. So this is going to be pi times, okay, the antiderivative of this we just showed was all of this. I'm going to make one slight change. Instead of writing this as 2 times x minus 1 to the negative 1 over negative 1, 2 divided by negative 1 is negative 2. And x minus 1 to the negative first is divided by x minus 1 to the first. So I would much rather write this part here as negative 2 over x minus 1. You don't have to do it that way. And then I've got plus 3 times the natural log of the absolute value of x minus 1 plus the natural log of the absolute value of x plus 4 plus the antiderivative of 2x e to the x squared, which was e to the x squared. All that from 2 to 5. What a mess. But we're almost done. So then we plug in 5. And we get pi times negative 2 over 5 minus 1. So negative 2 over 4. Plus 3 times the natural log of 5 minus 1. So 3 times the natural log of 4. You don't need the absolute values because the absolute value of 4 is 4. And then plugging in 5 here, the natural log of 9. plus e to the x squared is e to the 5 squared, so e to the 25. All of that minus, now I plug in 2. I get negative 2 over 2 minus 1, which is just negative 2. Plugging it, wow, I'll find out this. Plus 3 times the natural log of 2 minus 1 is 1. And then whenever you do an integral like this, you should say the natural log of 1 is 0, right? That's a pretty standard thing to do. And then the natural plus the natural log of 6 plus e to the 2 squared, which is e to the 4. And honestly, at this point, if I was doing this homework problem, I'd probably be done. But I don't want to do anymore. This is good enough. You don't need to simplify this any further. If you really, really felt compelled to simplify this further, there's not really actually a lot of simplifying you can even do. All I can really do here is add the constant, the integers together. So negative 1/2 plus 2 is going to give me a positive 3/2. You could, if you really felt compelled, you could put together the natural log of 9 as a minus natural log of 6. I don't feel so compelled. I'm just going to write this as 3 natural log of 4 plus natural log of 9 minus natural log of 6. And then finally, plus e to the 25th minus e to the 4th. There's no, I mean, you could put these together as like one gross natural logarithm, but who cares? This you can't do anything with. E to the 25th minus e to the 4th is just, that's it. I mean, if you, no, that's all I should say. That's it. There's nothing more you can do. So bit by bit, each individual piece of this is not by itself terrible. But if someone just gave you this problem to start with, it's kind of a lot to break down into its various pieces. So just be aware that sometimes something looks awful, but really if you just attack it one piece at a time, it's not that bad. It's still pretty bad. Okay. Yeah. Where's my other? Never keep track. Okay. Any questions about this before we move along? I'm definitely, when I saw this problem, to me, the hard part actually was observing that you could factor the bottom, right? I mean, if you see a fraction like that and you can't do a u sub, that's kind of your only other choice is to start trying to factor the bottom to be able to use partial fractions, but it can still be challenging if it's a higher power than a square power, right? To see how it factors, but you can just start plugging in numbers that are factors of 4 or whatever the number is that you have at the end there. All right. So not every class has probably started talking about it yet, but it is probably worth starting to talk about differential equations, which you will all already have been dealing with. Your teachers probably just haven't said that exact word. So I just want to point out what a differential equation is. A differential equation involves a function typically called y, but you can call it whatever you want, and one or more of its derivatives. It actually doesn't even have to have, this is probably not a very precise definition of what a differential equation is because you probably don't even have to have the function y, to be perfectly honest. So here's an example of a differential equation that you probably all would be comfortable solving. Here is my derivative of y equal to x squared. There's a differential equation. The derivative of my function is equal to x squared. The solution, so here's my diff EQ, my differential equation. And the solution to this differential equation is, well, I know how to find the antiderivative of x squared. It's x cubed over 3 plus a constant. I want to emphasize here that when you are finding the solution to a differential equation, it is the function that you were talking about. So your solution is a function. And this is the general solution here because I haven't specified what the constant needs to be. I could also do something like this. I could say, let's start with, we should start with a classic. Here's a differential equation. Y prime is equal to 3 times y. This one's a little bit harder. I'm not gonna lie. I'm also going to, we'll start with this and then we'll work on it. So how do we solve this differential equation? Well, I think it's easier to solve a differential equation like this if you rewrite y prime as a derivative using the other Leibniz notation, which is just the dy dx notation, or whatever your independent variable is, dy dx, often dy dt, because we were thinking of things as functions of time. In fact, in this class, especially dy dt, I would say. So it's probably better to think of this as dy dt equals 3 times whatever the function y is. And just write this one time, I'm going to write y of t. But usually we just write y. So whatever my function is, if I take the derivative of it, my derivative is going to be 3 times the original function. Which once you see the answer, you'll be like, oh, of course, that makes total sense. But it takes a minute to get to the answer. So how do we solve a differential equation like this? Well, in this class, actually, I don't know. I know we talk about separable, at least. I don't know if we talk about the other thing. So for sure, we can solve something like this, which is a separable differential equation. And separable just means you can get all the t's on one side, or whatever your independent variable is, and all the y's, or whatever your dependent variable is, on the other side, through multiplying or dividing. You can't add or subtract, and the reason you can't add or subtract really is because you have to also make sure that dy ends up on the left and dt ends up on the right. So if I was doing this, I would first say dy equals 3 times y times dt. So I certainly have all my t's on the right, but now I need all my y's on the left. So I'm going to divide both sides by y. So I'm going to get 1 over y times dy equal to 3 times dt. And then we're going to anti-differentiate both sides to be able to solve for y as a function of t. So we're going to integrate both sides. And then we're going to say, oh, the integral of 1 over y is the natural log of the absolute value of y. I'm going to say I'm going to keep the absolute value for now, but I'm going to tell you, for the most part, you can really just drop it. And you'll see why in a second here. Pun intended. All right, okay. So antiderivative of 3 is 3t plus a constant. So now we're going to solve for y, which we usually try to do. Sometimes you end up with differential equations where you can't actually solve for the function y because it's like some weird expression that just can't be solved. Like you've got too many y's to solve for. Here we don't. We've got one y. So to solve this, I'm going to exponentiate both sides. I'm going to say that e to the natural log of the absolute value of y is equal to e to the 3t plus c. Cool. E to the natural log of some stuff is just the stuff. You get the absolute value of y equal to, I'm going to fix this or make it better. E to the 3t plus c is really e to the 3t times e to the c. And this is where we start somewhat. E to the c, I don't know what the constant c is, but if whatever it is, e to a constant is still just another constant. Some people like to use the same letter. I kind of tend to like to use different letters. Especially in this situation, we often call e to the c capital A. So we're going to say that y is equal to a e to the 3t. Oh, absolute value of y is equal to a to the 3t. A can be positive or negative. I always mess up. So yes, brain. I've skipped one step. Sorry. Let me take. Sorry. There's one thing I want to say here. That was really the key. It's not really that important, but I want to say it. So before we get to there, let's say this: e to the c, always positive. So now I'm going to say y, though, on the other hand, could be positive or negative, right? Even though this stuff here is always positive, y can be negative and the absolute value of it would be positive. Or y can be positive and the absolute value of it would be positive. So here's what we're going to do. We're going to say, well, y could really be plus or minus e to the c times e to the 3t. And then we're going to say whatever this constant out in front is here, whether it's positive e to the c or negative e to the c, we're just going to call that a. What I really want to say is don't get too hung up on this. I'm trying to make it clear so that you don't have to worry about it later. You're like, oh, there's an absolute value there, but we just dropped it. Why did we do that? This is why we did that, because it works out. So when you're solving something like this and you get the natural value, the absolute value of y, like, don't worry about the absolute value. Just let it go. I'm trying to tell myself this. It's hard for me to follow my own advice here. I can't just let it go. I have to say it, but you all let it go and just get y equal to ae to the 3t. And that is the solution to this differential equation. So this differential equation, y prime equal to 3y, the solution is y as a function of t equals a times e to the 3t. Let's check that to make sure it makes sense. So I'm just gonna write it all down again. Not all of it. So our differential equation was y prime equals 3y, or preferably dy dt equals 3 times y of t. And our solution is y equals a constant times e to the 3t. But let's actually check. So if we take the derivative of that, so check. The derivative of y is y prime. The derivative of a constant times e to the stuff is constant just hangs out. And the derivative of e to the stuff is e to the stuff times the what of the stuff? The derivative of the stuff, which is 3. But look, that's your function, y of t. Right? Y of t is equal to a times e to the 3t. There it is, right there. So this derivative is equal to 3 times the original function. Exactly like we said it did to start off the differential equation. You have probably seen this differential equation before in some sense, maybe in 17a a little bit when we talk about exponential growth. Maybe, I don't know. Actually, I don't know. Do we talk about exponential growth in 17a? I don't remember. It doesn't matter. We're talking about it now. This is the model for exponential growth. So when you say that y prime is equal to 3 times y, what you're really saying is you're saying dy dt, the rate of change of y, or we usually think of y as like the population of some cells or some people or some deer or whatever, some biological thing. You're saying the rate of change of your population is 3 times, in this case, or in general, proportional to the population size. So what we're saying is the population is growing at a rate that is 3 times whatever the size of the population is. So if the population is larger, the population is growing faster, which makes sense, right? If we're thinking about, if you have more people, they're going to make more people. So this is an example of what's called exponential growth, when the rate of change is proportional to the size of the function, or the size of the population. So when you see this, this exactly corresponds to y equal to, in this case, a e to the 3 times t. Or more generally, if dy dt is a multiple of y, and the words you will often see here is the rate of change is proportional to the population. And again, just to be super duper explicit here, dy dt is the rate of change multiplying by a constant. That's where we're getting proportionality. And y itself is the population size at time t. That's what this equation represents. And when someone says the rate of change is proportional to the population, you should immediately think, oh, that means we have exponential growth or decay, right? You could have something that is, you could have rate of change that's proportional to population size and the proportionality constant is negative. That would mean the population is decreasing as time is moving on. That kind of situation usually comes up when we're talking about something like radioactive decay is a common example of exponential decay. But really, it doesn't matter if you say growth or decay, it's still the same equations. Cool. Questions? I have to make sure I'm saying the right words here. So every class covers differential equations, like the 16 series, the 21 series, the 17 series, in kind of a slightly different way. So I want to make sure I'm saying the right words for you all, as opposed to the different words. Yeah. Okay, sure. We should talk about this for a second. How much time have I got? All right. We'll do two things. Thing one are the words that get used in this class. So in this class, for some reason, they've decided, oh, no, it's not. There are biological names for things that I don't particularly know very well. So let's say that N of T, N gets used a lot in this textbook. Capital N of T is the population at time T. Population of whatever you want to think of. I think of people or cells typically because those are usual examples. And there are examples of things that often grow exponentially depending on the situation. So if we have dn dt equal to 2 times n, this is an equation, a differential equation, and it's called autonomous differential equation. And the reason it's called that is because it doesn't depend on time at all. Right? There is no time variable in the equation other than the dt right there. And it's interesting. No, I won't say that. So yeah, that's all. So basically, if your differential equation, more generally, if you have your derivative depending only on the dependent variable, that's autonomous. And again, these words don't really matter in that you don't need to know them to solve these things or to deal with these things. But sometimes teachers will ask you test questions like, is this differential equation autonomous or the other one of the other two things we're about to talk about in a second? Okay. And this one should have gone down here. Apologies. The second possibility is that your differential equation only depends on time. So maybe the rate of change of your population is equal to, I don't know, something like time squared. This is called a pure time. I mean, what a great name. Is a pure, I'm being sarcastic. It's not a great name. It's very unoriginal. It's a pure time differential equation. Because again, all we're saying here is that the rate of growth of this population only depends on the time variable, doesn't depend on the population itself, which in my opinion doesn't seem particularly realistic in a biological setting. For the rate of change of a population to not depend on the population itself seems, I don't know, my understanding of biology is not great, so maybe I'm way off base here, but it seems weird to me. I will point out here that you could solve this, right? We could say that dn is equal to t squared times dt, right? What we're doing here is what's called separating variables again, and then we could integrate both sides. The integral of 1 times dn is just n. The integral of t squared is t cubed over 3 plus a constant. So what our solution here would be is that the population, the size of the population of n at time t is just t cubed over 3. Which again seems weird to have a population growth that is unrestricted based purely on time. It seems unrealistic. Anyway, not the point. Finally, it's not finally. So generally we should say here that if your dn dt is equal to just a function of time, then it's pure time. Big surprise. And then lastly, the one that I think is kind of the most annoying is if you have something with both time and your population size or your dependent variable, it's called non-autonomous. It's also not pure time, but apparently that's obvious. So if you have something like dn dt equal to 2n plus 3t, it is non-autonomous. Or more generally, if dn dt is equal to a function of n and t, then it's not autonomous. I will point out this differential equation cannot be solved by separating variables. It is literally impossible. There is another method which I don't actually remember if we talk about in this class or not. Sometimes it depends on the teacher. I'll have to go back and look and see. But this is solvable through another method, which we may or may not talk about. Okay. So you should familiarize yourself with those terms. They're not that terrible once you realize that they just mean these different things. The last thing I want to say, because I know some people have a question about this, is, let me just grab this example. Where'd you go? Yeah, right there. So, no, not there. Where's the other one? Sorry. I know. It's always the one you want, you never find. Right? Where's this? I had the paper I wanted right in front of me. It disappeared because it always does. Fine. Oh, there it is. Ha ha ha. Found it. Good. Okay. So here's the other thing I want you to see. We want to, so something that you sometimes are asked to do is to verify that something like, I don't love the one I was looking at there. Sorry. There's another one I had. Brain it up. Or it's, okay, here we go. Sorry, 1 second. I know we've got 2 minutes. I can make it work. Cool. There we go. There, yes, okay, finally. Sorry. Okay. So verify that y equal to t minus t to the negative first is a solution to the differential equation, which often gets abbreviated like this, or just as dE. T times y prime plus y equal to 2 times t. These problems at first always seem harder than they really are. So here's what you want to do. Start with y equals t minus t to the negative 1. Look at your differential equation. Other than y, what other derivatives do I have? I have the first derivative. So find those, or maybe your differential equation has a second and a third derivative. Find all the derivatives that are in your differential equation. So I'm going to find y prime. That's not too terrible. I'm just going to take the derivative. It's going to be 1 plus t to the negative 2. And then after you found all the things that appear there, plug these in where appropriate. So let's see, if I plug those in, t times y prime, that's 1 plus t to the negative 2, plus y, t minus t to the negative 1. I actually don't want to say it's equal to 2t. I'm going to do the work to get to 2t. So if I actually simplify this, so t times 1 is t times t to the negative 2 is, I add the powers, I get t to the negative 1, plus t minus t to the negative 1. Oh, the t to the negative 1s cancel out because they're opposite signs. And then I'm left with t plus t, which is 2t. That's how you verify a solution to a differential equation. Is you start with the solution, typically. There are other ones that are a little weirder. But you start with it, you take all the necessary derivatives, and then you plug those in where they go to see if it actually gets you what you're supposed to get. It should always work if it says to verify. Cool.